and then nice method. That would be 4.7. Okay, we are going to sometimes there are two people done this type of equation, Cauchy, a French mathematician, and the Euler, the Swiss one. Okay, so that's a Cauchy-Euler equation. Half the time they refer to it as a Euler equation. You go with the Cauchy. See? Now, what's going to be the form of this equation? Look at this one. A linear, it must be a linear equation. Linear differential equation. Here, differential equation of the following form. Look at the form. It's going to be a constant like a times x squared. Okay, times x squared, but y double prime. Second order, plus it's going to be a constant times x y prime. And then you are going to have another constant cy. Okay, and it's going to be equal to the, let's say, g of x. We assume x is positive, x is a non-zero most of the time, or a positive, because x is going to be all over the places. So if x is going to be 0, okay, everything would be 0. So this is going to be the case. Of course, these are numbers. So where a, b, and c are going to be constant. Okay, c are constant. Okay, and the equation of this form is going to be called Cauchy-Euler. Okay, is said to be named. Okay, said to be a Cauchy-Euler equation. Cauchy-Euler equation. And there is another name for it. You see, look at these powers. You have x squared y double prime. You have the x y prime, and this is in fact x to the 0 y. So the powers and the orders are the same. Sometimes they refer to it as this expression. They call it, equidimension. Okay, dimensional, or dimensional. Okay, dimensional equation. Okay, so it's very easy to identify this equation. As soon as you see it, you'll be able to identify it. Now, we want to solve it. In order to solve this equation, it's a non-homogeneous. So what you have to do is you have to let it equal to the 0 first. You have to solve the homogeneous one. If you solve the homogeneous one, we get the YC. As soon as you get the YC, then you have to find the YP. In order to find the YP, okay, the particular solution, since the coefficients are not going to be constant, you have to use the variation of the parameter method, the method that we talked about the other day, to be able, to find the general solution. So this is this is going to be the plan. So here we are to solve this equation. Okay, to solve the Euler equation. I refer to it as Euler equation. You have to solve the homogeneous one first. Okay. This is going to be one. Let's say the particular, suppose you solve the homogeneous one. The particular solution, YP, this must be done by using the, variation of parameter method. Okay, the particular solution YP can be determined, can be defined, can be determined by the variation of the parameter method, by the variation of parameter method. So that would be YP. Now we're going to find the, so we need to find the YC. Okay, so our job is going to be, so V or one should find. Okay, one should solve the resulted corresponding, or we call it complementary. Okay, so complementary equations, homogeneous equation, which is going to be the following: a x squared y double prime a plus b x y prime plus cy equal to 0. Okay, we have to solve this one to get what? To determine or to find YC. If you got it, then you know that. Then y equal to YC plus YP would be the solution of the equation. It's going to be the general solution. Of the equation. So that's the plan. Okay. So now we change it to the homogeneous and we focus on the homogeneous. Okay, there you are, solving homogeneous Euler equation. Which is this one. I repeat it again: ax squared y double prime bx y prime plus cy equal to 0. You see, remember the way we solve the homogeneous equation with the constant coefficient? We forced the solution. We forced the solution to be something like e to the rx. We did similar one at the beginning of the course. For this type of equation, we are going to force the solution to be x to the r, not e to the rx. Okay? So we assume that the solution is x to the r. Then what we are going to do is, it must satisfy the equation. So we find the first derivative, r x to the r minus 1. We find the second derivative, r times r minus 1, x to the r minus 2. We substitute here, everything will cancel out. The result would be a nice quadratic equation. We solve it, we find the r, we come back. But the point is going to be, when you get this type of equation, you are going to have three possibilities: real solutions, repeated solution, and the conjugate solutions. So in each case, you have to determine the shape of the solution. A couple of them are going to be different. You should be paying attention, okay? So this is it. This is the way we're going to do it. So assume that this is it. We force the solution ourselves, and then we get the condition. So suppose you assume, suppose I'm going to find a condition that guarantee that x to the r is a solution. Suppose that r is a number. Okay, is a number. R is a number, and y equal to x to the r is a solution of the equation. Okay, is a solution of that equation. Okay, of the equation. Then get the derivative. Okay, get the derivative of this function. Drop it into the function. Drop it into the equation. There you go. Find the derivative. So y is x to the r. So y prime would be r x to the r minus 1. Y double prime would be r times r minus 1 x to the r minus 2. So all the derivatives that we have. If this is supposed to be the solution of the equation, it must satisfy. Drop them into this equation. Okay, so go back to the equation, substitute. We have ax squared already. Now substitute for y double prime. Y double prime is r times r minus 1, x to the r minus 2. Go to the second one, plus b times. We've got b times x. Replace y prime by r x to the r minus 1. Okay, plus c times y. But y is x to the r. This must be 0, because you claim that this is the solution of your equation. Okay. Now simplify these x's. Look at the x. This is x to the r minus 2, and this is x squared. When you multiply them together, you see that gives x to the r. This is x, and this is x to the r minus 1. That gives x to the r, and that gives x to the r. In the case of the previous case, remember, they were all e to the rx, e to the rx, e to the rx. In this case, it's going to be x to the r. So rewrite it. So we are going to have a r minus 1, x to the r, plus b r x to the r, okay, plus c x to the r equal to this. Remember, x is a non-zero number. X is positive. So x to the r is not 0. And then you are going to divide by x to the r. Okay, drop it. So when you drop it, what's going to be the result? Start with the easy equation to handle. Okay, they give you AR times R minus 1. That's BR, okay, plus C equal to the 0. It's going to be result of the equation. So multiply the first one. Okay, multiply the R inside, so that gives you A times R squared minus R. And this is going to be BR plus C equal to the 0. Continue. So that gives you AR squared minus AR plus BR plus C equal to the 0. I'm going to write it down in the form of the quadratic equation. So the final answer is going to be AR squared. I'm going to factor out the negative sign here and the R. So that gives me A minus B times R. And the C equal to the 0. That's it. This is going to be a characteristic equation corresponds to the homogeneous Euler equation, like the one that you know. You can memorize it, but the way I do it, I don't memorize this one. I just substitute. That's very easy to substitute. As soon as you substitute, you know you can drop all the x's. You know that it's going to be x to the r all the time. It would be easier. But anyway, if you want to memorize it, this is going to be the characteristic equation. Okay. So this is going to be called the characteristic equation of the Euler equation. Now we have a tool, if you like. So x to the r is going to be a solution of the Euler equation if and only if r is going to be a zeros of a quadratic equation. Then there are 3 possibilities. You have to consider 3 possibilities and list the result for us, and then we're done. Okay, any question? So I go to the next page. So set it up. So this is it. The result is going to be, we can claim that, note that, that's a conclusion. Note that y equal to x to the r is a solution. Okay, is the solution, a solution of the Euler equation. This one, of course. Euler equation. Okay, if and only if. If and only if r is a 0, a root. R is a root of the so-called characteristic equation. Characteristic equation. The one that we just proved. AR squared minus A minus B times R plus C equal to the 0. Now consider those 3 possibilities and check the result. Okay, there are 3 possibilities. three cases or possibilities. Again, as usual, case one, if we get distinct solutions. Okay, distinct, different. Okay, the case one, distinct, real roots. We refer to the roots for the equation, quadratic equation, okay, and the solution for the differential equation. So in this case, suppose you solve that equation and you get two solutions. You call it R1 and R2, exactly as we did it before. Okay, so suppose R1 not equal to the R2 are going to be solutions are okay. So these are going to be two solutions. Okay, I refer to that star equation, which is somewhat quadratic one, characteristics one. Okay, you know that if this is going to be the case, you have two solutions. Then y1 corresponding solution y1 x to the r1 and y2. Okay, and y2 x to the r2 are going to be what? These are going to be our solutions. Our solutions okay, of the differential equation. You can check it with this condition. With the condition that the Wronskian y1 comma y2 is not equal to the 0. It's very easy to check the Wronskian because you already got, you remember Wronskian is y1 y2 prime minus y2 prime. You get just the powers of x. Since x is positive, that part is going to be, you can write it down if you would like to see it. You see this is going to be the Wronskian of y1 and y2. It's going to be what? It's going to be y1, y2 prime minus y1 prime and y2. See, if you substitute right as is, y1 is x to the r1. Okay, y2 prime is what? Is r2 x to the r2 minus 1 minus y1 prime is r1 x to the r1 minus 1. Okay, times the second one is going to be x to the, okay, that gives you x to the r2. So these are going to be the case. We can factor out if you like to show that the leftover is going to be a non-zero number. Okay, it's not going to be a big deal. To prove that's going to be non-zero, you see this is x to the r minus 1. So we can factor out something like x to the r minus 1, x1. Sorry, all of them are. Yes, this is going to be x to the r minus 1. And then factor out x to the r2 minus 1. See, if you factor out all these, what's going to be the conclusion? The conclusion is going to be to get these factor out from this part. See, x to the r2 minus 1 would be out, so that gives you something like r2x. Okay, this is going to be the case, and for the other one, would be something like r1. This is going to be r1x. So these are going to be the values. Okay, I think that's great. So since r2 and you can factor out even that x extra 1. So everything is going to be a non-zero number because r2 and r1 are disjoint, all of them. So the difference is never 0. I think that's correct. Yeah? So I just factor out this is x to the r minus 1. So the leftover is going to be x over here. And then the other part is going to be the same thing because this is x to the r2. It's going to be the same thing, okay? So eventually this is going to be a non-zero number because r1 is not equal to the r2. And x is a possible number. Okay, so the Wronskian is going to be a non-zero number, and you know that if the Wronskian non-zero number, so this means therefore YC or Y. YC would be what? Would be C1 x to the R1 plus C2 x to the R2. This is going to be your general solution. Okay, that's case one. So as soon as you see there's two different numbers, you go for it, right? The one that we did before. You need to worry about. The second part is a little bit different. After the second one is if you get a repeated solution. Okay, so repeated, you get repeated real solution. Real solution or solutions. Now, suppose R1 and R2 are the same. So if R1 is equal to the R2, in this case we call it R, is a repeated solution. It's a repeated root, if you like, root of the star equation, characteristic equation. Then you know that automatically you are going to have one solution. Then y1, you can call it y1 equal to the x to the r is a solution. Is the solution of the differential equation. Now remember, you can use the what? You can use the reduction of the order. Yes.
If R1 is equal to R2, wouldn't that make the Wronskian 0?
For this one?
For the previous one, you have R2x minus R1x, or does that not apply?
No,
here?
in the previous part, R1 and R1, we use it because R1 and R2 are different.
Okay.
You know it, that was the condition.
Okay.
Okay, but for this one, so for this, you cannot have two solutions like the previous part.
Okay.
So you have
It's
to
just
find
one
something
solution.
else. Okay. So what we're going to do, remember that the second solution is going to be V times Y1, and then you go to the reduction of order formula, you find the second solution. Okay. So it's going to be a solution, a differential equation, and one can apply. Okay, you can apply the reduction of the order method. Okay, method to find the second solution. Show that I give it the second solution. Show that the y2, see the second solution will be of this form. X to the r, ln of x. Use that method. You know that it was one integral of 1 over y1 square integral of e to the negative px dx. If you do it, that gives you the second solution. Okay, show that the y2 equal to the x to the r ln x is also, okay, is also a solution of the, differential equation, or the second one of the differential equation. Okay, don't believe it, just apply it yourself. Get it? Okay, so there you are. Therefore, in this case, what's going to be the YC? The one that we have to memorize and use it. So YC would be what? YC would be, the first solution is x to the r plus, sorry, it's a C1. C1 x to the r plus, okay, plus what? C2 x to the r ln of x. So this is going to be your general solution for the second one. Because the solutions are x to the r and x to the r ln x. So linear combination of these two, C1 x to the r plus C2 x to the r ln x, it's going to be the result. Some people, they factor out that x to the r, but they don't have to. Just write it down as is to get this information. Okay? So that is the second case. Any question? Yes.
Why is y2 x to the r ln x?
Why?
Why?
You can prove it.
No, it's all right.
No, it's because the solutions are repeated.
You see,
Okay, that's what I was
you,
thinking.
you have to, I talk about it, don't prove. You can prove it yourself.
Okay.
You know the formula.
It's like how you foil in another X.
No,
kinda
no,
like
no,
the
no.
other
You,
one.
you have to, you know that. You have if I have the y1, we want to find the y2. Remember, y2 would be what? By the reduction of all the
It's
method.
y2 equals vy1, so that's your v.
Vy1, then
Okay.
the v would be integral of
Everything.
1
Yeah.
over y1 squared e to the k.
Okay, so
Yeah, if you do it, you get that.
okay.
Okay, but we believe it. That's going to be the case. So this is going to be the second type. Any question? Complex one would be lots of fun to write it down. Okay, let's see what's going to be complex. Okay, and in your field, or if you do some application problems in future, it's always the complex ones that's come around. Okay, so pay attention to the complex. Again, we just use the Euler formula to write it down in those formats that you know it. So the third case about complex roots. Complex roots. Again, you know that the complex roots are coming in pairs. It's going to be alpha plus or minus beta I, okay? And it's going to be two different solutions. You can consider the one, but I'm going to prove it. Something similar to the one that we remember. Previously, we did have solution of going to be e to the alpha x cosine of the beta x, e to the alpha x sine of the beta x. But you have to modify it a little bit to get it. That's the second part would be different. So let's see, work out the algebra so that we get it. So that's it. Suppose we have the solution. Okay, suppose. So the solutions are going to be of the form of R1 equal to the alpha plus beta I, and the R2, which is going to be alpha minus beta I. Okay, suppose these are going to be two complex solutions, two complex solution or roots of that characteristic equation. Okay, a star equation means that characteristic equation that we have. Okay, again, you can write it down. There are two different solutions. So what is going to be the general solution? As a two different solution, the general solution are going to be what? I write it down, then I simplify it for you. I don't want to be surprised. Okay, so what is going to be YC this time? YC would be again C1. The first solution, e to the C1 x to the R1, remember? It's going to be C1 x to the R1 plus C2 x to the R2. But if you substitute, that gives you C1 x to the what? Alpha plus beta I. And this is going to be C2 x to the alpha minus beta I. Okay, that's going to be the one. Now we're going to do a little bit of algebra. Change using the Euler formula to change this complex type. So I'm going to work on one of them, then come back and simplify it. So look at this one to see what we can do from that Euler formula. Okay, so as we did it before, x plus alpha I, you can write it on as x to the alpha. Okay, x to the alpha times x to the beta I. Okay, that is going to be the case. Now I'm going to use that complex form. So what we can do is, I'm going to rewrite this one as x to the alpha. X to the alpha, I want to change this one into the exponential form. Remember, the way we write on the exponential form is going to be e to the ln of x to the beta I. Because ln function and the e function are inverse of each other, okay? So these two would cancel out, you get that x to the beta I. I want to write down in the formula, that if I have e to the beta I can write cosine of the beta plus I sine of the, beta x plus I sine of the beta x. So I just change it to this format, now I'll be able to do it. So this is going to be x to the alpha, e to the. Okay, so what I'm going to do is I'm going to bring that power down. I bring the beta I down. So that give me what? It's going to be beta I times ln x. Okay, I bring the power down. So this is going to be x to the alpha, e to the I times beta ln x. Got it? Now I write down the sine and cosine. Going to be equal to what? This is x to the alpha. The Euler formula. The Euler formula, e to the I data is what? Is cosine of the data plus I sine of the data. That's Euler formula. Okay? Now we do the same thing here. So what's going to be the result? X to the alpha times what? Yes.
It says is theta equal to b ln of x.
Beta equal to what?
Is theta equal to
Yeah. So it's going to be what? No. It's going to be x to the alpha times what? Cosine of, see cosine of the beta ln x. Beta ln x plus I times sine of beta ln x. See, that would be a situation that we are going to have. Okay. So what we did all together, this is it. So basically what we did here is that x to the, okay, remember this was what? This was just x to the beta I that we started. So going back, the solution are going to be of this form, okay, x alpha. We just did this one for one of them. But as we did it before, if you get back to your equation, see the first one is alpha plus beta, the second one is alpha minus beta. So you know that the cosine of the negative data and the cosine of the data are the same. In the case of the sine, you just bring the negative sign outside. So it's going to be almost the same thing when you put it with this constant that we're going to have. The second one would have only a negative sign extra. That negative sign would be embedded in the constant. So basically, this means those particular solution that you're going to have. See, the conclusion is going to be, say that therefore, this is going to be the way you're going to have. You can consider your y1 in this form to be x to the alpha cosine of the beta ln x. It's going to be your solution, okay, one of the solution, and you consider your y2 to be equal to the x to the alpha sine of the beta of ln x. Okay, because this is your C1 and the other one is C2. Both of them are going to be the same. And this is going to be a general solution now. So YC is going to be C1 Y1 plus C2 Y2. And in this case, YC would be X. It's going to be C1 X to the alpha cosine of the beta ln x plus C2 X to the alpha sine of the beta times ln x. This would be the general solution of your differential equation. It's very much like in the case of previous one, remember you did have e to the alpha x cosine of the beta x, e to the alpha x sine of the beta x. Yes.
For the last, or for the line before therefore, how do we get rid of that I in the second term? How does that I
is going to be a constant. Because when you write it down together, you'll see this is going to be kind of a linear combination you're going to have.
Okay, so the I's will cancel out.
No, not cancel out. It's going to be embedded in your, in that constant term that you put here, C1 and the C2.
I
Because it's going to be C2I.
So,
Okay, you call it C2.
okay, so those C's are imaginary numbers to an extent. The constants, possibly, maybe.
They are going to be constant. It may be imaginary, maybe otherwise.
Okay.
It depends on the nature of the problem that you have. That is not going to be important, you see, because this is a linear equation. When it's a linear equation, see when something is linear. Have you done linear algebra? Okay. If it's going to be linear, your space would be what? Would be closed under addition and a scalar multiplication. So this means if y is in your set, then alpha times y is also in your set. So if I times y2 is your solution,
That's also.
divided by I,
It's a,
y2 is also a solution. Because we imagine that you are in a space of what? You are in a space of all the solutions
that exists.
of this differential equation, and you're just creating a basis. Okay, so
That makes sense.
you just want to be classic.
Yeah.
Just leave as is. But that's what it is really. Because you can extend it. This is just order 2. You can have the higher order. See, higher order, right? All of them together. It's a very nice construction that we have. Okay, so make sure to remember it nicely when you want to write it down. This is, use parentheses here is the cosine of the beta of the ln x, sine of the beta x, and listed as one of those formula, and you have to bring it in. That's it. I give a break. Let's solve the problem. We need to solve a couple of them to see. It takes a little bit of time. You have to manage your time to solve one. Yeah.
So over here.
That's why you were saying.
Yeah.
You're still down for that?
I'm always down for that stack.
Yeah, you have one. You get one.
Okay, and also, I like didn't put down the YC because I didn't meant to. So I was like, I didn't know.
Highlight
Show
when I'm
all
like,
the evidence.
look back.
Okay.
No, because I've already been.
Well, I really
Play
I like that you have the
play,
line.
Transdifferent.
You know what the three colors are.
Okay. So even though I got YP correct, I had to show Y. Okay, it's fine.
Let me just change that.
Okay,
They're pretty colors. Yeah.
exactly. I was up.
That's my whole rainbow. You know what that reminds me of?
Do it again.
Oh my God.
Are we reading this again? What?
I try to do it tonight. If you don't see it by tomorrow night,
Okay.
just send me an email.
Okay.
Very good.
Okay.
This is your.
Is this support material or is it just normal? Video?
Yo.
Brother?
Yeah.
Yeah. Oh, they told me.
Yeah.
You're a mesa or
Yeah.
someone you're really in a battle bot?
We are.
Yeah, no what?
Oh, we were converting rumors into battle bots.
Or like part of what, like maker club?
Yeah,
or-
the big club. Yeah. And we're trying to present the street festival, but unfortunately, it's not really happening here. We can do that at elementary.
Elementary school?
Yeah.
All right.
So at their street festival. I heard you guys wanted to make a go-kart.
A go-kart? I was thinking about it. Soapbox? Like soapbox racing?
Yeah.
Like racing down hills? So it's like there's no motor or anything, you just steer 'em down hills. I kind of want to do something like that with,
Yeah.
like over the summer or something.
Should I do that, but I put a motor in it?
Didn't Rebel do that?
Yeah.
Yeah.
Yeah, but then it gets like a little tricky because then you gotta like actually fit sprockets and stuff on. They can get it to like spin wheels. Dirt bike. I was thinking the motor out of the dirt bike and then putting it in a go-kart.
The Honda?
I have a KTM.
Oh, shoot.
Don't know.
It comes off super easy. That support material you said?
Oh, not supports. It's just supports.
Why is it so easy to take off?
I'm using orchestra.
Damn. You might have to download it tonight.
It's your turn to. Guess who's? Devin, Sierra.
It looks like a P.
The recycle
This is an
supports?
AirPod. I feel like
Nothing's-
Sierra would be fun. Sierra. And this is Michelle.
Short, of course.
Oh, four of four. I'm gonna try.
I'm so hungry, bro.
Pretty same. I haven't eaten anything. I was busy all day.
What'd you do?
This. I have to go to Cup 3.
I've just been sitting all day.
I have to study for.
It's like the first day in 3 weeks where I've not been studying. It's been nice. Been enjoying
A bunch of club stuff. Just been busy with that.
it. We gotta do some research stuff for the computer science.
That's what we talked to you about.
What are we gonna do?
Some.
Some Arduino stuff. Let's teach everyone how to code in C, embedded. Just teach them. Yeah,
So I think we lose in an hour, don't we?
it's easy.
Yeah, it's spring forward, solve that. Oh, wait, no. Wait, I'm pretty sure we.
Yeah,
Spring forward.
No, we
get
Daylight savings.
Yeah.
You save this shit for Monday.
Yeah, we get an extra hour, no, we lose an hour of sleep, but
Yeah,
we
they
get an hour of sunlight.
Wait, when is that?
I'm gonna appreciate.
This weekend,
Sunday.
yeah, right, it happens.
I kinda like it.
It's like it goes to 2 AM and then it goes back to 2 AM.
I'm God, funny.
You're gone. No, I think it was like 1:59 and then it
You
goes
see
to.
my outfit right now?
Yeah.
Really like that.
It looks like. Yeah, it's a nice. Well,
I know,
watch
that's-
it.
Yeah. No, that's still fun.
I once had a flight
Oh,
the
dude.
day that daylight savings happened, and it was like I had to get up at
Going to
3
work
a.m.
on
and I was
topic
like, what
somewhere,
if 3 a.m.
okay,
never
first
happened.
opportunities, then none.
I was so
One
stressed
is
out, I
very
didn't think I
good
slept.
Example,
Sleep in there.
solve each equation. Euler equation, we're going to do this Euler, but you can, kind of understand. Solve each equation. This is the first one. First one is x squared, y double prime, minus 2x, y prime, minus 4y equal to 0. This is homogeneous Euler equation. Because it start, you see, x squared, y double prime, x, y prime, no. So, homogeneous, the way I do it, I substitute x to the r to get the characteristic equation. Don't like it, that formula that we prove for you, a r squared. But it's safe, you see, to substitute really, but you have the option. So this is the way I do it. I let y equal to the x to the r. So y prime would be r x to the r minus 1. And y double prime would be r times r minus 1 x to the r minus 2. Drop it into the equation. Okay, into the equation that give me x squared. Okay, r times r minus 1 x to the r minus 2 minus 2x r prime r x to the r minus 1. Okay, minus 4y x to the r equal to 0. All the x's will disappear because that would be x to the r. Okay, drop the x's. That give you your equation. Because if you put them together, that give x to the r, and you can cancel out x to the r. So the leftover is this one, r minus 1, minus 2r, the last one minus 4, equal to the 0. Simplify it, that give you your equation. So it's going to be r squared minus r minus 2r minus 4 equal to 0. So combine the like terms. R squared minus 3r minus 4 equal to 0. This is your characteristic equation. The way I do it, to memorize anything. Okay, factoring method gives us the solution right away. So it's going to be r minus 4 times r plus 1 equal to 0. So we have two solutions. You can label it r1 and r2 as you like. I call the r1 to be equal to 4 and the r2 to be equal to the negative 1. So I have two distinct solutions. For each solution, x to the r is your particular solution. Okay, and the combination is your final answer. So y is equal to the c1. Okay, c1 x to the 4th power plus C2 x to the negative 1. So that is going to be the final answer. Easy equation to solve. Let's make sure you don't miss any sign, something. If you get to the quadratic equation, the situation will be different. Okay? That's a type 1. Any question? Let's get the type 2 type. Type 2. Type 2 is this one. 4x squared. Okay, 4x squared y double prime plus 8x y prime plus y equal to this. Again, it's Euler equation. Okay, x double prime y prime, x squared y double prime, x y prime, and the constant. Okay, go for it. Substitute, get the characteristic equation. Like this one. X equal to the r, the solution, y prime, r, h to the r minus 1, double prime, r times r minus 1, h to the r minus 2. Drop it into the equation, cancel out the x's to get your r. So from the equation that give you 4x squared, okay, so that gives us 4x squared y double prime, which is r times r minus 1. Okay, x to the r minus 2. Next one is going to be 8 times x, 8x y prime, r x to the r minus 1, and plus the y, which is x to the r, equal to the 0. Okay, cancel out all the x's. Here. So the leftover is going to be 4r. 4r times r minus 1 from the first one, 8r from the second one, and the plus 1 from the last one. Simplify 4r squared minus 4r plus 8r plus 1. Equal to 0. Combine the like terms. So that give you 4r squared plus 4r plus 1 equal to 0. It's a perfect square, can factor it. Because this is the square of the 2r and this is the square of 1. So that gives you 2r plus 1 all squared equal to 0. So 2r plus 1 equal to 0. So r equal to the negative half is a repeated solution. Okay, it's a repeated solution. Okay, be careful, make sure to get it right. And we know that in this case, the solutions are x to the r is one of them, x to the r ln of x is the other. X to the r, ln x. So r is negative. So there you are. This is going to be y equal to c1. When we c1, x to the r, x to the negative half, plus c2. C2 x to the negative half, but times it by ln x, because the repeated solution. Okay, and the repeated solution, the first solution x to the r, you can use the reduction of order formula to find the other one. Okay, that's case 2. All these possibility, when you get to the big one, which is a non-homogeneous one, it can happen. Situation is quite different for each one of them because you have to go to the method of the variation of the proposition. Okay, so we need one more for the complex, and then we go to the non-homogeneous. Any question? So let's see what would happen with the non-complex, non-real case, or the complex roots, which is a kind of a more popular one for application problems. So that's a number 3. Number 3, you have x squared y double prime, okay, plus 3x y prime, 3xy prime plus 3y equal to 0. This is going to be your equation. Again, it's Euler equation. So again, check x to the r in the equation. So the solution is going to be, so the possible solutions are y equal to the x to the r, y prime is r x to the r minus 1, y double prime is r times r minus 1 x to the r minus 2. Drop it into the equation, then remove those x's and get your characteristic equation. Okay, so there you are, x2. Got the x2, r times r minus 1, x to the r minus 2. Then you have plus 3x, y prime, r x to the r minus 1. That's 3y, which is 3x to the r. Okay, equal to this. Drop the x's. So this is it. The leftover is going to be r times r minus 1 from the first one, 3r from the second one, and 3 from the last one. Simplify by the like term to get that quadratic equation. So it's going to be r squared minus r plus 3r plus 3 equal to this. By the like terms, so that give you r squared plus 2r plus 3 equal to this. That would be your characteristic equation. It's not factorable. The two numbers with the product of 3 and the sum of 2. So that was, so get the quadratic formula to see if the solutions are going to be complex. Okay, so when you're ready for it, you may have to use the formula. So there you are. So r is equal. I'm going to use quadratic formula. Okay, set negative b plus or minus. Negative b would be negative 2 plus or minus b squared, which is going to be 2 squared, minus 4ac. 4, a coefficient of r squared is 1. C divided by 2a, 2 times 1. Okay, that's a quadratic formula. Simplify inside the radical. So it's going to be equal to the negative 2 plus or minus inside. 2 squared would be 4. Minus 3 times 4 would be 12. That gives you 2. So inside the radical is going to be a negative number. It's going to be plus or minus a radical negative 8 over 2. You switch the negative 8 into the 8i squared and you work it, okay? So it's going to be equal to, you have a negative 2 plus or minus the square root of 8i squared divided by 2. It's not a perfect square, but 8 is 2 times 4. So this is going to be equal to, okay, it's going to be equal to the negative 2 plus or minus. It's going to be 2 radical 2 radical 2i over 2. Okay, because radical 8 is 2 times 4. So you put out the 4, you write down as a 2 radical 2, I is outside. Now you break it, you have to break it to identify the alpha and beta, remember? You need alpha and beta. So we go on. So that gives you negative 2 over 2 for the real part, plus the negative 2 radical 2 over 2 times I. Now you simplify it. So simplify the first one, that give you a negative 1. Okay, the first one give you a negative 1, and the second one give you positive negative radical 2i. So this is going to be your r. Consider the positive, and we identify the alpha and beta. You don't have to consider both of them we talk about. We prove it. Okay, so the characteristic equation, this solution is going to be negative 1 plus radical 2i. Compare it with the alpha and beta I. So your alpha would be negative 1, and your beta would be radical 2. Now you are ready to go to the formula that we have. Remember, the formula was this one. I repeat it for you. It's a C1 x to the r cosine of beta ln x. That's a C2 x to the, okay, sorry, x to the alpha. This is x to the alpha, because we have the alpha and beta. Okay, C2 x to the alpha sine of the beta ln x. It's like e to the alpha x that we had before. Now you substitute, so it's going to be y equal to the C1, alpha is -1. X to the -1 cosine of the beta is radical 2. Radical 2 ln x. That's the first part. That's C2 x to the -1 sine of the radical 2 ln of x. So this would be the final answer. So in case of the complex, you have a little bit more to do. Just make sure you are ready for it. Okay, any question? So that's a homogeneous one. So we usually give you one question, a couple of parts of this homogeneous, because we want to check all the three conditions, three cases. And then we check one of them with the non-homogeneous case. Okay, there are some very famous non-homogeneous one in application in science. You're dealing with the Euler equations, okay? It's coming from different modeling, So that would be our next example. Any question? So they were all homogeneous. Now, the non-homogeneous. That's it. So it comes most of the time with the sine, cosine, exponential function. These are part of the deal. Okay, and then, next practice one. We post that one very much for you over the weekend, so you can have a look. Big steps for the variation of parameter and these techniques. So give you time to think about it. Then of course we go over it. Okay, there you are. Solve this equation. Okay, solve the equation is x squared y double prime minus 3x y prime, okay, plus 3y. 3y is equal to the 2x to the 4th e to the x. And they give you the condition that x is possible. Have this condition all the time. Size. There you are. It's a non-homogeneous equation. You know that. You have to solve the homogeneous one first. Okay, you let it equal to the 0. Go with your equation, you do the job, you come back. Then in order to get the particular solution method, only variation of the parameters. You cannot use that constant coefficient one because and determinant coefficient, because the coefficients are not numbers. There is one nice problem if you like problems. In the way they do it, in some books, they prove that you can use a special substitution, like the one that you use for remember the homogeneous equation, Riccati equation, etc. You can use a special substitution to change this equation into new equation with the constant coefficient. Then you stay with that constant coefficient. Then you find the relation. That would be nice, if you like problems, but we just stay with the standard method. Okay, so if you see it somewhere, don't be surprised. It's a standard. Okay, so let's solve the homogeneous one first. Okay, solve this equation first. X squared y double prime minus 3x y prime plus 3y equal to 0. You have to solve this one this time to get the yc. So go for it. X to the r, just bring your solutions. So y x to the r, y prime r x to the r minus 1. Okay, y double prime is r times r minus 1, x to the r minus 2. Drop it into the equation, remove the x's, form the Cauchy equation. So this is it. It's going to be x squared y double prime, which is r times r minus 1, x to the r minus 2, then minus 3xy prime, which is r x to the r minus 1, okay, plus 3y, 3x to the r, equal to the 0. Okay, remove the x's. So x would be out. Get the leftover and continue. So the leftover is going to be r times r minus 1 from the first part, minus 3r, the second one, and the 3 equal to the 0. Simplify, combine the like terms to see what type of equation do you have. Okay, so we are going to have the r squared minus r minus 3r plus 3 equal to the 0. And the like terms that give you r squared minus 4r plus 3 equal to the 0. It's factorable. Two numbers product of 3 and the sum of 4. So the numbers are r minus 3 times r minus 1 equal to the 0. So we have two solutions. Okay, I call r1 to equal to 3. The first one, and I call the r2 to equal to. So the YC is C1 x to the R1 plus C2 x to the R2. So it's going to be C1 x cubed, the first one, plus C2 x to the first part. So this is going to be your YC. Any question? Now we have to find the YP. Okay, so the next question is going to be, what is YP? In order to get the YP, we are going to use the variation of the parameter method. Okay, variation of the parameter method, and you know that in that variation of the parameter, we're going to call the YP to be equal to the U1 Y1 plus U2 Y2. Okay. And you have to know the formula for the U1 and the U2. But before going on, you have to make sure that you have what is going to be your R of X. You see, remember when you use variation of the parameter in the equation, coefficient of the Y double prime must be 1. So your R of X, you go back to this equation, look at this one. R of X as is 2x to the 4 e to the x. But in this case, the coefficient is x squared. So since you want to use the variation of the parameter, this is the time that consider R of X to be 2x to the 4 e to the x divided by x squared. You don't need the other part of the equation to divide everything by x squared for the equation. But now that you want to determine what is your R of X, do it here. It's always the case because it's Euler equations. It must start with the x squared. Okay, if the next step, the integral getting badly, complicated, you probably miss the Rx. Okay, all the time, you have to divide it. Otherwise, some of the integral is going to be impossible to find. So identified here, you see, is going to be the original one, 2x to the 4 e to the x, okay, divided by x squared, the coefficient of the Y double prime. So the R of X that you're going to carry from now on is going to be 2x squared e to the x. Any question? So you don't have to go back and divide. And some people, they do it right at the beginning, then they be confused when they want to substitute x to the r, getting those. Don't touch it. Just when you get to the R of X over here, it's not divided by whatever coefficient it is. It's x squared, maybe 2x squared, 5x squared, okay? Now we are ready to operate operation for the finding the U1 and U2. You know that you have to find the Wronskian first, the formulas. So we identify the Y1. So our Y1 is going to be x cubed. Our Y2 is going to be x. Okay, this is it. And we want to find those formula. See, I just remind you, remember the U1, for example, is what? U1 is a negative Y2. We proved the formula the other day. R of X divided by the Wronskian. Okay, this is the formula that we proved the other day. Okay, for you. that is going to be, that's the U1, Y1, but the negative sign is here. And when it's a U2, it's going to be Y1 out of X. Okay, that is, just remind you know yourself. So that is going to be the case. Of course, the X. So you have to find the Wronskian first. So differentiate Y1 prime. Y1 prime would be 3x squared, and the Y2 prime would be 1. Yes.
So it's negative y2 and then positive y1.
That's it,
Okay.
Yeah, the way we proved it the other day, it's going to be this. Okay, so we go with the Wronskian. So the Wronskian of the Y1, Y2, remember, is the Y1, Y2 prime minus Y1 prime, Y2, the determinant of that matrix. The other day, substitute, carefully substitute, the Y1 is x cubed. So that's going to be x cubed, Y2 prime is 1. So it's going to be x cubed times 1 minus Y1 prime. Y1 prime is 3x squared. Okay, times Y2. Y2 is x. Okay, so that gives you x cubed minus 3x cubed. So the result will be negative 2x squared. Okay, and it's a non-zero.
2x cubed.
Sorry? Negative 2x cubed, yes, thank you. Okay, originally x is not 0, so because you know that the Wronskian must be non-zero to be able to continue. X is not 0, it's positive, so this is going to be non-zero, so we are saying. Now we can go and form the U1. So what's going to be U1? U1 is equal to the integral of negative Y1, Y2. Y2 is x, negative x, times R of x. You see R of x, the simplified one. So R of x is what? Is 2x squared, 2x squared e to the x. Divided by the Wronskian. The Wronskian is a negative 2x cubed. Then the dx. Now simplify. This case is nicely simplified. At the top would be 2x cubed. You see that's going to be the top. Again, is going to be negative 2x cubed e to the x. And the bottom one is negative 2x cubed dx. So simplify the x cubed. So it's going to be integral of e to the x dx. E to the x dx is e to the x. Remember, no constant c, because you are working for the particular solution. It's not the general solution of your equation. Okay, any question? Most of the time you may end up with the integration by parts here, okay? So you should repeat. Most of the time can be done with the table one. Okay, so that's going to be U1. So repeat it again for the U2. So U2 formula is Y1 R of x. Okay, integral of Y1. Y1 is x cubed, so it's going to be x cubed. Okay, times R of x again, which is going to be 2x squared e to the x, and divided by the Wronskian, which is a negative 2x cubed. Negative 2x cubed, and the dx. Okay. Now simplified. To multiply the top, we can cancel out this x cubed and x cubed, 2 and negative 2. So this is going to be negative. Okay, it's going to be negative x squared e to the x dx. You can pull out the negative sign, so it's going to be negative x squared e to the x dx. So you have to find this integral, and you know that you can do it by using the table. After the method to find the x squared e to the x. Okay, remember how we can find it? So I go to the next page to remind you. Any question? So it's unavoidable. You see this step. It's come with the sine, cosine. There are a couple of cases with the secant at the tangent. You may even end up with the secant. You should remember what's the integral of a secant?
Negative natural log of cosine.
No?
No, that's tangent.
Integral of secant x.
Tangent plus secant.
That's it, yeah. It's a natural log of the secant plus tangent or tangent plus secant. Okay. So you will see it. There is couple of examples that you end up with the secant. So remind yourself, okay, let's have the formula available. So I'm going to continue here to get it. So I'm going to find this integral first. Okay, x squared e to the x dx, then I multiply by -1. And that's it. So using that Cauchy-Euler method, this is it. So differentiate, integrate, sign is positive, start with the x squared, and this is e to the x. So it's going to be minus, differentiate 2x, integrate again e to the x. Positive, that give you 2, e to the x. Negative, that give you 0, and e to the x. Okay, so you put them together. So the integral of x squared e to the x dx, or just a negative, it's going to be negative. So that give you x squared e to the x, the first one, minus 2x e to the x, the second one, that's 2e to the x. So that is the case. You apply the negative sign, of course, it's going to be negative x squared e to the x, that's 2x e to the x, minus 2e to the x. Okay, remember this is going to be what? This is our u2 now. So you have the u1 and the u2. Of course, you have to go back and find the yp. The yp is u1 y1 plus u2 y2. Okay, so we continue with finding the yp. So yp would be u1 times y1 plus u2 times y2. So it's going to be equal to the u1 was easy, u1 just e to the x. That's just e to the x, and the y1 is x cubed. But plus u2, okay, plus u2, which is this, times the y2, and the y2 is x. So it's going to be x times negative x squared e to the x plus 2x e to the x minus 2e to the x. You have to multiply, simplify it. So this is going to be x cubed e to the x, and this is going to be minus x cubed e to the x, and this is a plus 2x squared e to the x, and minus 2x e to the x. So these two would cancel out. So would cancel out. So eventually yp, your yp is going to be 2x squared. Okay, the yp will be 2x squared e to the x minus 2x e to the x. This is going to be your yp. Now we can go back and give you the solution of the equation. So the solution of the equation is y equal to the yc plus yp. And your yc was c1 x cubed plus c2 x squared, and the yp 2x squared e to the x minus 2x e to the x. This is going to be the solution of the Euler equations. Okay, it takes times when you want to solve one of them. There are a couple of tricky ones regarding the ln function. I go with that practice one. See, I posted, so just practice to see quickly to see that integral, resulted integral. Make sure you know able to. Yes, that's question.
Should it be c2x to the first?
C2x to the
First.
you are right, thank you. C2x to the, okay, that is going to be the case. Okay, when you have a repeated solution, you've got to be a little bit careful for this. Because when it's a repeated solution, your y1 would be something like x squared ln x, then you want to take those two into the run scan and get it to the u1 and u2, then you get some equations that it takes time, but it can be done. Nicely, it can be done, nothing to worry about. You have quite a lot to practice. Okay, that's it. This is Cauchy Okay, Cauchy-Euler equation that we're going to have.